Hey everybody, today's lesson is going to be about
second derivative.
You thought that was better than the last one? Should we go one more time or are we good?
I don't care.
Okay.
We can go.
Okay, that's good. Get down.
I don't care.
On the count of three. 1, 2, 3. Hey everybody, today's lesson is going to be about
The second derivative.
We got it that time. So as before mentioned, we're going to be talking about the second derivative today, and these are notes that are in the link that you can find right on the course calendar. For the second derivative, I want to remind you that the second derivative tells us how the rate is changing. So imagine that we've got a function that looks like this, and then we've got a function that looks like this. Both of these functions are increasing. The difference is that if you look at the rates on this one, see how the rates are getting steeper here. So remember that concave up refers to the second derivative being positive, and the reason is because the rates are increasing. Whereas if you had something like this, while the function is increasing, the second derivative would be negative because the rates are getting smaller. Right. So this comes into play when we study a function like so. Now, one of the things that we know right away is that when you have an integral function like g of x is the integral from 2 to x of f of t, you want to note that this right here is the rate of change of this. And if we come on down here, I actually gave you a graph of f. So let's note that what we're looking at is the rate itself. So if I asked you, where is g of x, not f, but g of x going to be concave up? What you would say is that concave up equals the rate increasing. So if this is the rate is increasing here and here and here. So we would expect on those intervals that the function would be concave up. Also, if I asked you for the points of inflection of the original function, you'd say, well, the points of inflection, I'm going to draw a picture over here, would be where we change from one concavity to the other. And so that means that that's a point where we go from the rate increasing to the rate decreasing, or vice versa. So look at this graph. Where does the rate change from increasing to decreasing? Well, right there, it was increasing, now it's decreasing. Right here, it was decreasing, now it's increasing. Right here, it was increasing, now it's decreasing. So there, and then there, and then there. So the points of inflection of the original function will happen at the maxes / the mins of the rate function. Okay. So with that in mind, let's actually draw a graph of g of x. So now I'm actually going to draw a graph of g. And I know that if I plug 2 into this function right here, that would be an integral from 2 to 2. And the integral from 2 to 2 is 0. So I know that this function has a value of 0 right here. I also know that the amount of change in this function will be equal to the areas under the curve because it's an integral. So right here, I know that it's going to go up by 4, and then up by 4, and then down by 4, down by 4, down by 4. So I'm going to come here, and I'm going to go up by 4. Oh, that's 3. Boop. I'm going to go up by 4 more, and then I'm going to go down by 4, down by 4, and down by 4. In the backwards direction, I need it to go down by 4, up by 4, up by 4. So if I do this, and then do. Now it'll go down by 4, up by 4, up by 4. Okay, so there's our graph. Now notice that we probably don't want to just connect like this. We want to figure out what the concavity will be. And that's where we can look at the graph that we just drew. We know that because the rate is increasing on this interval, we want concave up. So this needs to be concave up. Okay, the other place where we want concave up is from 2 to 4 and then from 8 to 10. So I'm going to come up here and from 2 to 4, concave up, and from 8 to 10, concave up. Everywhere else, the rate is decreasing, so it should be concave down, concave down, concave down. And there is the graph of G. Called the second derivative test. And that means identifying what sort of extreme values you have based on the value of the second derivative. So let's go through a few examples. First one, this is all about 3. Suppose that the first derivative is 0 at 3. So if this is x equals 3, and I know that the first derivative is 0, and then this says that the second derivative is 2. Well, that's a positive number, and that tells us something about the shape. It tells us that it's concave up. So the curve must look like that at this instant. Therefore, if you have this is 0, first derivative 0, and second derivative positive, you know you're going to have a local maximum. Likewise, let's suppose we had a similar situation where here's our point, and we know that the first derivative is 0, so you got a critical point, and then the second derivative is negative. The negative tells us that the curve will be concave down, which ensures that we are going to have a local minimum. Okay, next one. Let's suppose that the first derivative is this, it's 2, so it's not 0, and then the second derivative is positive. You might be tempted to say, oh, well, this is going to be a local max because the second derivative is positive, but that's actually not the case. What's going on here is that you have a curve that is concave up, and then since the first derivative is 2, you're going to have a positive slope like this, and you can see that this point right here is going to be not an extreme value. So in this case, we have neither a max nor a min. Finally, this is the weird case. Let's suppose that the first derivative is 0, and that the second derivative is also 0. In that case, there's really 3 different things that can happen. You might have a situation that looks like this. It's a plateau. That's what would happen if you had, say, like x cubed is your function. In this case, it would be neither. However, if it was something like x squared, it would look like this, and you would have a max. And if it was something like negative x squared, it would look like this. Oh, sorry, minimum here, maximum here. The point is that if the second derivative is 0, the answer is not neither. It's that it might be neither, it might be a min, or it might be a max. So in this situation right here, this tells you that the extreme value cannot be determined. Let's look at a function where we know the first and second derivative values. I've marked that we have 1, 2, 3 critical points because there's 3 points where the derivative is 0. Let's see what we can figure out using the second derivative about the types of extrema. Well, the second derivative is positive here at -3, so that means that it'll be concave up. That means that this right here should be a minimum. Let's come over here. Right here, the second derivative is negative. That means concave down, which means that this point will be a max. And this point right here, the second derivative is 0, so it cannot. So let's take an example where we're working with a function. This right here is the first derivative. So this is the rate, and we're only interested when x is greater than 0, and I want you to identify the extrema. So that means that I want you to identify the maxes and the mins. Well, the first thing that you need to know in order to find the maxes and the mins is you need to know where the critical points are happening. So step 1 is going to be find your critical points. Well, critical point means that the derivative is 0 or that the derivative is undefined. So what would make this derivative 0? Well, derivatives are 0 when their numerators are 0. So this would be the solutions to this equation right here. And it only has one solution, and that solution is x equals e. So there's one critical point. What would make a derivative undefined? That will happen when the derivative is 0, or when the denominator is 0, because you can't divide by 0. So 0 is equal to x squared, which means x is 0. Now these would be our two critical points, except for that the problem says we're only interested in x greater than 0. So I'm going to cross this one off. Also, well, we won't go down that way. All right, so now I want to know whether x equals e is a maximum or a minimum. And we're going to take a different route than we usually do. We're going to use the second derivative test. That means that we are going to take e and we're going to plug it into the second derivative and figure out whether we have a curve that is concave up or concave down at that point. So first you need your second derivative. So our second derivative using the quotient rule would be x squared gets squared in the denominator. Numerator would be x squared multiplied by the derivative of the numerator is negative 1 over x minus derivative denominator times numerator. We take that and simplify it. So this becomes negative x minus 2x plus 2x, natural log of x, all divided by x to the 4th. You will notice that all of the terms in the numerator have an x, so I'm going to simplify them such that our second derivative will be negative 3 plus 2 natural log of x all over x cubed. Basically, I took one of the factors of x here, and I canceled it with this one, and this one. So there's our second derivative. Now, we're going to plug e into this because we're interested in whether e is a local maximum or a local minimum. When we do that, all right, natural log of e is 1. So our numerator, hey girls, I'm recording a video. So try not to sound like feral animals. So we get negative 1 over e to the 3rd, which is less than 0. What does that tell us? That tells us that at x equals e, we have a curve that is concave down. Therefore, x equals e is a local maximum. Now, I'm a mind reader. I am an absolute mind reader. I know what is going on in your brain right now. You are thinking to yourself, Mr. Klein, this second derivative test is an awful lot of work. Can't I just use the first derivative test from first semester? And the answer is that on this problem, you could. And the first derivative test would look like this. So, it would change the problem so that step 1 would be this. Step 2, first derivative test, you would make a sign chart. You would put e on that sign, and then you would have to figure out that the derivative is negative over here, and positive over here. Because if you plug something larger than e into the natural log, it makes this larger. 1 minus something larger than 1 is negative. And that would lead you to a local max. So this is an example of a problem where you could use the first derivative test, or you could use the second derivative test. Now let me show you one where you don't have a choice. This time we have a diffie-q. The derivative is equal to 2 times the x value plus the y value. And we know that it passes through the point 1, negative 2. And we want to know whether this point right here is a minimum, a maximum, or possibly something that is neither, like right there. Okay, so this is a two-step problem. The first is you need to figure out whether this is in fact a critical point. So I'm going to take the derivative and I'm going to plug 1 comma negative 2 into it, getting 2 times 1 plus negative 2, which is equal to 0, which means, yes, we are dealing with a critical point. We know this is a point where the slope is 0. So step 2 is to apply the second derivative test. In order to do that, we need the second derivative, which would be the derivative with respect to x of 2x plus y, which would be, we're going to need to take this implicitly, the derivative of 2x with respect to x is 2, plus the derivative of y with respect to x is either dy dx or y prime. So I'm going to place y prime with what it's equal to, which is this right here. So let's grab that. Let's bring it down, circus style. Let's plug it in right here. 2x plus y. Now, if I take our expression for the second derivative and I plug in the point that we are interested in, I get 2 plus 2 times 1 plus negative 2, which is 2, which is a positive number. That tells us that this thing is going to be concave up. Therefore, we know we are dealing with a local minimum. On this one, because we're dealing with points that have an x and a y value instead of just an x value, you literally cannot use the first derivative test because you can't make a sign chart. To extend the problem, let's suppose that this differential equation also passes through 3, negative 2. And again, we want to know whether this is a minimum, a maximum, or perhaps neither. One of the things you really have to be careful about on these problems is making sure that you always start by checking that we have a critical point. So in the case of this one, if you plug 3, negative 2 in, you get 2 times 3 plus negative 2, which is equal to 4. Or in other words, the slope at the instant that we are talking about is pretty steep. It is positive 4. And I don't even know what the concavity is, but it doesn't matter because if it's concave up, we get a point like this, which is neither. And if it's concave down, we get a point like this, which is still neither a maximum or a minimum. So if this number right here is not 0, then you have neither a max nor a min.